Java Debugger architecture. Here you can see Java platform debugger architecture. JDB helps you find and fix bugs in Java language programs. The Java debugger JDB is a simple command line debugger for Java classes. It is a demonstration of the Java platform debugger architecture that provides inspection and debugging of a local or remote Java virtual machine. Here you can see the structure overview. The Java platform debugger architecture is structured as follows here. What is the Java platform debugger architecture? JPDA. JPDA is a multi-tiered debugging architecture that allows developers to easily create debugger application which run probably across platforms, virtual machine implementation and JDK versions. JPDA consists of 3 layers: JVM TI, Java VM tool interface, defines the debugging services a VM provides, JDWP, Java debugging via protocol, defines the communication between Debuggee and the debugger processes, JDI, Java debug interface, defines a high-level Java language interface which tool developers can easily use to write remote debugger applications. Reference implementation. In addition to the specification of these interfaces, Oracle also provides a reference implementation which consists of JVM TI implementation on multiple VMs, backend which uses JVM TI to implement the Debuggee side of the JDWP, front end which uses the debugger side of JDWP to implement JDI. Two simple example debugger applications which are built on JDI. This provides a layered implementation in which any layer must be substituted. Using JPDA, a debugger developer may look into JPDA at any layer. Since the JDI is the highest level and easiest to use, we encourage developers to use this interface. Suppose a company develops a debugger using JDI, they can use it with the reference implementation and it will automatically work with the VMs and platforms that Oracle supports. It can also work for example with the reference implementation front end and a Debuggee running another company's VM that implements JDWP, which might use or bypass JVM TI. Some debuggers are built on top of lower layers JDWP. For example, if the front end is not written in Java language, or JVM-TI for specified specialized debuggers which need low-level functionality. Components. Debuggee. Debuggee is the process being debugged. It consists of the application being debugged, not shown here, the VM running the application, and the backend of the debugger. Java virtual machine, VM. This refers to the VM running the application being debugged. The debugger architecture is being designed for use in wide spectrum of VM implementations. The VM implements the Java virtual machine tool interface, JVM-TI. Backend. The backend of the debugger is responsible for communicating requests from the debugger frontend to the Debuggee VM, and for communicating the response to these requests, including desired event, to the frontend. The backend communicates with the frontend over a communication channel using the Java debug via protocol. The backend communicates with the Debuggee VM using the Java virtual machine tool interface, JVM-TI. It is clear from experience that debugger support code running on the Debuggee and written in Java contains with the Debuggee in ways that cause hangs and other desired behavior. Thus, the backend is native code. This in turn implies that the JVM-TI be pure native interface. Communications channel. The communications channel is the link between front and back ends of the debugger. It can be thought of as consisting of two mechanisms. A connector. A connector is a JDI object, that is the means by which a connection is established between front and back end. JPDA defines three types of connectors. Listening connectors. The front end listen for an incoming connection from the back end. Attaching connections. The front end attaches to an already running backend. Launching connectors. The front end actually launches the Java process that will run the Debuggee code and the backend. Transport. Transport is the underlying mechanism used to move bits between front end and back end. Transport mechanism is used to transfer mechanism used is unspecified. Possible mechanisms include sockets, serial lines, shared memory. However, the format and semantics of serialized bit stream flowing over the channel is specified by the Java debug via protocol, JDWP. JPDA includes service provider interface that allows the development and deployment of connector and transport implementations. These service provider interfaces allows debugger and the other tool vendors to develop new connector implementations and provide addition transport mechanisms over and beyond the socket and shared memory transport provided by Oracle. The service provider interfaces in JDI are specified in the com.sun.jdi.connect.spi package. In addition to the service provider interfaces in JDI, JPDA also defines a transport library interface called Java Debug via Protocol Transport Interface. A transport library is logged by the JDWP agent in the target VM and is used to establish a connection to the debugger and to transport JDWP packets between debugger and the VM. Front end. The debugger front end implements the high-level Java debug interface JDI. The front end uses the information from the low-level debug via protocol JDWP. User interface UI. The user interface to the debugger is not specified. The intent is that tool vendors will provide value-added implementations. We provide an example, simple graphical user interface GUI, which serves as a test harness and as a starting point for development of more complex GUIs. The version of JDB is also available as an example. The example UIs are client of the Java debug interface JDI. Debugger interfaces. Java virtual machine tool interface. A native interface implemented by VM defines the services a VM must provide for debugging. Includes requests for information, for example current stack frame, actions, for example set a breakpoint, a notification, for example when a breakpoint has been hit. A debugger may make use of VM information other than this. The example Java native interface JNI, but this is the source of all debugger specific information. Specifying the VM interface allows any VM implementer to plug easily into debugging architecture. It also allows alternative communication channel implementation. VM implementation which do not adhere to this interface can still provide access via the Java debug via protocol JDWP. Java debug via protocol JDWP defines the format of information and requests transferred between Debuggee process and the debugger front end. It does not define the transport mechanism, socket, serial line, shared memory. The specification of the protocol allows Debuggee and debugger front end to run under separate VM implementations and or on separate platforms. It also allows the front end to be written in a language other than Java, or Debuggee to be non-native, for example Java. Information and requests are roughly at the level of Java virtual machine debug interface JVMTI, but will include additional information and requests necessitated by bandwidth issues. Examples include information filtering and batching. Java debug interface JDI, the 100% Java interface implemented by frontend, defines information and requests at the user code level, while debugger implementers could directly use the Java debug via protocol JDWP or Java virtual machine tool interface JVMTI. This interface greatly facilitates the integration of debugging capabilities into development environments. We recommend the JDI layer for all debugger development. Here you can see components. VM and backend are with Debuggee. Here the com channel. Here VM interacts with backend. Backend interacts with front end via here front end, and front end interact with UI. Here JVM TI Java VM tool interface is connected to Debuggee here. Here JDWP Java Debug Wire Protocol is connected to comp channel here. Here JDI Java Debug interface is connecting to this here. Here you can see JPDA architecture, Java Platform Debugger architecture. The Java Platform Debugger architecture JPDA is a collection of APIs to debug Java code. The Java Debugger interface JDI defines a high-level Java language interface that developers can easily use to write remote debugger application tools. Java Virtual Machine Tools interface, a native interface that helps to inspect the state and to control the execution of applications running in the Java Virtual Machine JVM. Java Virtual Machine Debug interface, JVM DI. JVM DI was deprecated in Java in J2SE 5.0 in favor of JVM TI and was removed in Java SE6. Java Debug Wire Protocol JDWP defines communication between Debuggee Java application and debugger process. Java Debugger interface JDI. JDI is a highest layer of the Java Platform Debugger architecture. It allows to communicate. It allows to access JVM and the internal variables of debugged program. It allows to set breakpoint stepping and handle threads. Here you can see Debuggee app, JVM TI in Debuggee. And here JVM TI interacts with JDI via JDWP, and JDI and Debugger UI are in Debugger here. Here you can see JPDA architecture. The Java Platform Debug architecture JPDA describes a set of API functions used for debugging Java applications running in a Java virtual machine. JPDA describe the following main APIs represented on different levels. Here you can see another view of JPDA architecture, the structure. Java Debug Interface JDI a high-level API used by a debugger to debug Java applications in a target JVM. JDI connectors and transports an auxiliary API for attaching to a target JVM in a different ways using different transport channels from a debugger side. Java debug via protocol JDWP, a specification of a protocol used for communication between debugger and the JDWP agent loaded on the JVM process. JDWP transport interface, an auxiliary API that specifies way to use different transport channels from the JDWP agent side. Java virtual machine tool interface, JVM TI, a low-level API exposed by a JVM to a JDWP agent or any other agent to control execution of a running Java application and provide access to its data. This figure illustrates the JPDA structure. Here, debugger, JDI implementation, connectors, and transport are inside debugger VM. Debugger VM is connected to JDI, and JDI interacts with JDI implementation. JDI implementation is connected to connectors. Connectors are connected to transport here. Transport in debugger VI interacts with transport in target VM here. Application VM core, JDWP agent, and transport are inside target VM here. Here send. Here application is connected to VM core. VM core is connected to JVM TI, and JDWP agent is connected to JVM TI, and AGWP agent is connected to JNI, and JNI interacts with VM core. Here JVM TI interacts with VM core. JDWP agent is connected to transport. Now we are considering debug Java anywhere case, and Java platform debug architecture delivers portability. The Java platform debug architecture uses a layered approach to connect debugger to an application. Debugger can be written in Java and run on same machine as the application under test, but it isn't a requirement. Any platform can host the debugger. Write once debug test everywhere is a variant on Java write once run anywhere claim, and it defined the Java platform debug architecture. JPDA is a client-server system built in 3 application programming interfaces: APIs, the Java debug interface JDI, is the client interface used by the Java debugger to access the debugging facilities. The JDI uses Java Debug Via Protocol JDWP class, Java Debug Via Protocol JDWP, which differs from the Java interface definitions associated with the other JPDA APIs. JDWP only defines the format of the packet passed between JDI and the Java Virtual Machine Debug Interface JVMDI. Along with the semantics associated with the data. This allows implementation to exploit any kind of transport mechanism in memory exchange between debugger and the application running on the same machine to TCP IP connections across the internet. Keeping the JDWP generic makes it relatively easy to build a debugger on any platform, not just Java. JVMDI tells a Java Virtual Machine JVM vendor how to implement the debugger interface to JVM. Hiding the application behind this interface lets the JVM be implemented in many ways, from Java bytecode interpreter to just-in-time JIT native code compiler. JPDA APIs can be implemented in Java, though it's not an requirement. Sun provides the JPDA library with the associated class and interface definitions. It's used with the Sun's JVM or compatible third-party JVMs. Embedded JVMs often implement the JVMDI and JDWP, with the JDWP supported by a transport mechanism such as TCP IP stack. In this case, the debugger is on a remote system, which is typical for embedded development environment. Pick your Java debugger. The advantage of JPDA is its ability to choose a debugger instead of being restricted to a particular Java platform. Often vendors matching debugger will have access to the additional VMs or operating system functionality. However, almost any debugger can handle application development. A number of Java debuggers suit with JPDA. Not surprisingly, Sun has some Java-based debuggers, and most commercial debuggers that provide the Java support use JDPA. There are also a number of open source Java debuggers, including one for Eclipse project. Another is JSWAT from the Blue Marsh Softworks. It's a standalone Java-based debugger that can handle applications on various platforms because it uses JDPA library. JDPA sits below the view of most developers, yet it's still very important component and key to Java's portability. It also gives developers choices that are unavailable through other development environments. Here you can see a non-Java based debugger. You can see the PC, debug application, JDI support, JDWP support, and TCP IP stack are inside here non-Java based debugger and PC. Debug application interacts with JDA support. JDA support interacts with JDWP support. JDWP support interacts with TCP/IP stack. Here TCP/IP stack interacts with TCP/IP stack in standalone JVM, and TCP/IP class in multiple JVM system, and here an TCP/IP class in JVM based debugger. Here Java application, JVM DI support, TCP/IP stack and TCP/IP stack are inside standalone JVM system. Here Java virtual machine. Java application is inside Java virtual machine here, and JVM DI Java virtual machine interacts with JVM DI support, and JVM support interacts with TCP/IP stack. TCP/IP stack interacts with TCP/IP stack in non-Java based debugger, and TCP/IP class in multiple JVM system, and TCP/IP class in Java based debugger. Here you can see a multiple JVM system, the Java virtual machine and Java virtual machine, another Java virtual machine here. Here JVM DI class, stub application, TCP/IP and TCP/IP class are inside Java virtual machine here, and Java application and JVM DI support are inside Java virtual machine here. Here JVM DI class interacts with the JVM DI support in other Java virtual machine here. Here JVM DI class interacts with Java application stub application. Stub application interacts with TCP/IP class. Here TCP/IP class interacts with TCP/IP stack in standalone JVM system, and TCP/IP stack in non-Java based debugger, and TCP/IP class in Java based debugger. Here Java application is inside Java virtual machine, and JVM DI support interacts with JVM DI class in other virtual machine. Here debug application, JDI class, JDWP class, and TCP/IP are inside Java based debugger here, and inside Java virtual machine. Debug application interacts with JDI class interacts with JDWP class, JDWP class interacts with TCP/IP class, TCP/IP class interacts with TCP/IP class in multiple JVM system, and TCP/IP stack in standalone JVM system, and TCP/IP stack in non-Java based debugger. Now we are focusing on Debuggee. The Debuggee is the process being debugged. It consists of the application being debugged, the VM running the application, and the backend of the debugger. We can here consider JVM tool interface. The JVM TM JVM tool interface, JVM TI, is a programming interface used by development and monitoring tools. It provides both a way to inspect the state and to control the execution of applications running in the Java virtual machine VM. Now we are focusing on VM. This refers to the VM running the application being debugged. The debugger architecture is being designed for use in wide spectrum of VM implementations. The VM implements the Java virtual machine debug interface, JVM TI. Here you can see a JVM architecture diagram. A virtual machine is a software implementation of a physical machine. Java was developed with the concept of WORA, write once, run anywhere, which runs on a VM. The compiler compiles the Java file into a java.class file. Then that .class file is input into the JVM, which loads and executes the class file. Below this is a diagram of the architecture of JVM. As shown in this architecture diagram, the JVM is divided into three main subsystems: class loader subsystem, runtime data area, and execution engine. Class loader subsystem. Java's dynamic class loading functionality is handled by the class loader subsystem. It loads and links and initializes the class file when it refers to a class for the first time at runtime, not compile time. Loading. Classes will be loaded by this component: bootstrap class loader, extension class loader, application class loader are the three class loaders that will help in achieving it. Bootstrap class loader, responsible for loading classes from the bootstrap class path, nothing but rt.jar. Highest priority will be given to this loader. Extension class loader, responsible for loading classes which are inside the ext folder, jre /lib. Application class loader, responsible for loading application level class path, mention, environment variable, etc. These class loaders will follow delegation hierarchy algorithm while loading the class files. Linking. Verify. Bytecode verifier will verify whether the generated bytecode is proper or not. If verification fails, we will get the verification error. Prepare. For all static variables, memory will be allocated and assigned with default values. Resolve. All symbolic memory references are replaced with the original references from method area. Initialization. This is the final phase of class loading. Here all static variables will be assigned with the original values and the static block will be executed. Runtime data area. Runtime data area is divided into 5 major components. Method area. All the class level data will be stored here, including static variables. There is only one method area per JVM and it is a shared resource. Heap area. All the objects and their corresponding instance variables and arrays will be stored here. There is also one heap area per JVM. Since the method and heap areas share memory for multiple threads, the data stored is not thread safe. Stack area. For every thread, a separate runtime stack will be created. For every method call, one entry will be made in the stack memory, which is called stack frame. All local variables will be created in the stack memory. The stack area is thread safe since it is not a shared resource. The stack frame is divided into 3 sub-entities. Local variable array related to the method how many local variables are involved, and the corresponding values will be stored here. Operand stack. If any intermediate operation is required to perform, operand stack act as a runtime workspace to perform the operation. Frame data. All symbols corresponding to the method is stored here. In the case of any exception, the catch block information will be maintained in the frame data. PC registers. Each thread will have a separate PC register. To hold the address of current execution instruction. Once the instruction is executed to the PC register, will be updated with the next instruction. Native method stacks. Native method stack holds native method information. For every thread, a separate native method stack will be created. Execution engine. The bytecode which is assigned to the runtime data area will be executed by the execution engine. The execution engine reads the bytecode and executes it piece by piece. Interpreter. The interpreter interprets the bytecode faster but executes slowly. The disadvantage of the interpreter is that when one method is called multiple times, every time a new interpretation is required. Just-in-time compiler. The GIT compiler neutralizes the disadvantage of the interpreter. The execution engine will be using the help of the interpreter in converting bytecode, but when it finds repeated code, it uses the GIT compiler, which compiles the entire bytecode and changes it to native code. This native code will be used directly for repeated method calls, which improve the performance of system. Intermediate code generator produces intermediate code. Code optimizer responsible for optimizing the intermediate code generated above. Target code generator responsible for generating machine code for native code. Profiler, a special component responsible for finding hotspots, that is whether the method called is called multiple times or not. Garbage collector collects and remove unreferenced objects. Garbage collections can be triggered by calling system.gc method, but the execution is not guaranteed. Garbage collection of the JVM collects the objects that are created. Java native interface, JNI. JNI will be interacting with the native method libraries and provides the native libraries required for the execution engine. Native method libraries. This is a collection of the native libraries which is required for the execution engine. Here class file is connected to class loader subsystem. Linking, loading, linking and initialization is inside class loader subsystem. Bootstrap class loader, extension class loader and application class loader are inside loading. Bootstrap class loader is connected to execution class loader. extension class loader. Extension class load is connected to application class loader. Loading is connected to linking. Verify, prepare, and resolve are inside linking. Verify is connected to prepare. Prepare is connected to resolve. Linking is connected to initialization. Class loader subsystem is class loader subsystem interact with runtime data areas. Method area, heap area, stack area, PC registers, and native method stacks are inside runtime data areas. A number of threads are inside stack area. Each thread has stack frame, LVA, local variable array, and operand stack, and frame data inside each thread. There are PC registers for each thread here, and runtime data areas are interacting with the execution engine. Interpreter, just-in-time compiler, garbage collections are inside execution engine. Intermediate code generator, code optimizer, target code generator, and profiler are inside just-in-time compiler. Intermediate code generator is connected to code optimizer. Code optimizer is connected to target code generator. Execution engine interacts with native method interface. Runtime data areas are interacting with native method interface. Native method interface interacts with native method library. As an example, we can consider this one, JDB my class. The most frequently used way is to have JDB launch a new Java virtual machine VM with the main class of the application to be debugged. This is done by substituting the command JDB for Java in the command line. For example, if your application's main class is my class, you use this command to debug it under JDB. When started this way, JDB invokes a second Java VM with any specified parameters, loads the specified class, and stop VM before executing that class's first instruction. JDB helps you to find and fix bugs in Java language programs. As an example 2, we can consider this. This command will run the my class application and allow JDB to connect it at a later time, and you can then attach JDB to the VM with this command. Dash attach address option attaches the debugger to the previously running VM using the default connection mechanism. Here agent lib dash agent lib colon jdwp. This option loads the JPDA reference implementation of JDWP. This library resides in the target VM and uses JVM TI and JNI to interact with it. It uses a transport and JDWP protocol to communicate with separate debugger application. And here the transport, name of the transport to use in connecting to debugger application, here DT. This here address, the transport address at which to listen for the newly launched target VM to connect. This value is typically part of the raw command argument as well, but this is not required if the target VM has some other means of determining the transport address to which it should connect. Here the address sub option, here the server sub option. If Y listen to for a debugger application to attach, otherwise attach to the debugger application at the specified address. Suspend if Y VM start event has a suspend policy of suspend underscore all. If N VM start event has a suspend policy of suspend underscore none. As an exception example, we can consider this situation. When an exception occurs for which there isn't a catch statement anywhere in the throwing threads call stack, the VM normally prints an exception trace and exits. When running under JDB, however, control returns to JDB at the offending throw. You can then use JDB to diagnose the cause of the exception. As an error example, we can consider this: failed to connect to remote VM, connection refused. This occurred. This is occurred in Eclipse IDE. Now we are focusing on backend. The backend of the debugger is responsible for communicating requests from the debugger frontend to the Debuggee VM and for communicating the response to these requests, including desired events, to the frontend. The backend communicates with the frontend over a communications channel using the Java debug wire protocol JDWP. The backend communicates with the Debuggee VM using Java Virtual Machine Debug Interface JVM TI. Here you can see a JVM TI architecture, and agent controls a JVM through JVM TI. Both share the same operating system process. The Java Virtual Machine Tool Interface JVM TI is the interface offered by the Java VM for its manipulation and control. Originally called Java Platform Debugger Architecture (JPDA) and used in the context of debugging, it was extended to support other use cases such as monitoring and profiling. JVM-TI exposes C functions to manipulate Java VM. The JVM-TI client, so-called an agent, queries and controls the given JVM, and agent share the same operating system process. JVM-TI agents are meant to be written in C to be as compact as possible and allow maximal control with minimum instruction. JVM-TI provides introspection and some limited intercession facilities at VM and language levels. In particular, it provides memory and heap management, thread control, execution task manipulation, object and class manipulation, and breakpoint support. JVM-TI is used mainly for debugging, monitoring and analysis purposes, particularly profiling and thread analysis. Here you can see a agent is here. Agent is connected to JVM-TI. Control is passed from agent to JVM-TI. JVM-TI is inside VM. Agent, VM and applications are inside monitored VM. Here you can see agent, application and VMs are in the operating system process. As an example, we can consider this. This is in C language. Hash include jvm-ti.h. Agents can be written in any native language that supports C language calling conventions and C or C++ definitions. The function, event, data type and constant definitions needed for using JVM-TI are defined in the include file jvm-ti.h. To use these definitions, add the J2SC include directory to your include path and add hash include jvm-ti.h to your source code. Here the jvm-ti.h include file for Java virtual machine tool interface. As an example too, we can consider this code, this one in C language. The get source debug extension for the class indicated by KLASS, return the debug extension via source underscore debug underscore extension underscore ptr. The returned string contains exactly the debug extension information present in the class file of KLASS. This one may only be called during the start of the live phase. As an optional functionality, might not be implemented for all virtual machines. Here the KLSS in J class type, the class 2, this is the class 2 query, the source underscore debug underscore extension underscore ptr in character asterisk. The agent passes a pointer to a charge string. On return, the charge string points to a newly allocated array. The array should be freed with deallocate. As an example 3, we can consider this one in C language, this code segment. If an agent is started during the onload phase, then its agent library must export a startup function with this prototype. This will be called early enough in the VM initialization that system properties may be set before they have been used in the startup of the VM. The full set of capabilities is still available. Note that capabilities that configure the VM may only be available at this time. No bytecodes have executed, no classes have been loaded, no objects have been created. The VM will call the agent underscore onload or agent underscore onload agent lib name function with options as second argument, that is, using the command line option examples, option 1, option 2 will be passed to the char asterisk options argument of agent underscore onload. The options argument is encoded as a modified UTF-8 string. If equal options is not specified, a 0 length string is passed to options. The lifespan of the options string is the agent underscore onload or agent underscore onload agent lib name call. If needed beyond this time, the string or part of the string must be copied. The period between the agent underscore onload is called, and when it returns is called the onload phase. Since VM is not initialized during the onload phase, the set of allowed operations inside agent underscore onload is restricted. The agent can safely process the options and set event callbacks with set event callbacks. Once VM initialization event is received, that is, the VM init callback is invoked, the agent can complete its initialization. The return value from agent underscore onload or agent underscore onload and underscore agent lib name is used to indicate an error. Any value other than 0 indicates an error and causes termination of the VM. As an example we can consider this one, the basics to find trace info in C language. Inside the agent itself, there is a trace info struct, and the pointers to these structs will serve as the value of the object tags. A tag is any 64-bit value. Along with the trace info struct is support code to create a hash table for quick lookups. Because the creation or lookup of trace info will probably consume much application time when this agent is activated, speed and efficiency are important. Here are some basics to find trace info. If thread equal null, that usually means that the VM initialization has not yet occurred, so you cannot get a stack trace. Calling get stack trace could also return an error message that the VM is not in the live phase, but a value jvmti underscore error underscore none indicates that you did not get a stack trace. Performing lookup or enter of this stack trace into the hash table will return a reference to a trace info structure. This pointer to a trace info struct will then be used as the tag on this object. All objects allocated from the same stack trace will have the same tag. When saving away stack trace information, pay attention to the trace info struct and the number of stack traces received. There should be only one stack trace of an allocation bytecode, new array bytecode, and but how many stack traces will that be? It depends on the application, but it's somewhat limited. Also, no cleanup is occurring in lookup or enter, so a very long running application could experience some problems if the total number of allocation traces is very high. The hash table is also a fixed size. Another potential problem: to avoid performance issues, being aware of the crucial sections, one of which is the lookup or enter function is crucial. Using too many crucial sections could dramatically slow the entire application. The thread used here is the current user thread, limited what you are doing in these threads. The object allocations and object free events are fairly crucial section free with regards to this particular agent. VM ti underscore event underscore VM underscore init. After the VM underscore start event and approximately several hundred class load events, the VM will reach the fully initialized event. That is about initialization. Here the thread could be null in some situations, so be careful. Here the request stack trace. If you get a pace error, the VM isn't ready or it died. If error not equal vmti underscore error underscore none, you have a serious problems. Here look up this entry here, look up or enter. If thread equal null, it's assumed that this is before VM underscore start, but technically this should not be should not happen. No tracking yet. As an exception, here we can now we are considering agent command line options in instruction in JVM TM tool interface. So here dash agent lib name equal options. The name following dash agent lib colon is the name of the library to load. Lookup of the library, both its full name and location, proceeds the platform in a platform specific manner. Typically the agent lib name is expanded to an operating system specific file name. The options will be passed to the agent on startup. For example, if the option dash agent lib colon foo equal opt1 opt2 is specified, the VM will attempt to load the shared library foo.dll from the system path under the Windows TM or libfoo.so from the ld-library-path under Linux. If the agent library is statically linked to the executable, then no actual loading takes place. Now we are considering agent startup onload pace. Other pace is live pace. Here, if an agent is started during the onload pace, then its agent library must export a startup function with the following prototype. Or statically link agent named L with the following function. The VM will start the agent by calling this function. It will be called early enough in VM initialization that system properties may be set before they have been used in the startup of VM. The full set of capabilities is still available. Note that capabilities that configure the VM may only be available at this time. No bytecodes have executed, no class have been loaded, no object have been created. The VM will call the agent onload or agent onload agent libname function with options as the second arguments. That is, using the command line option examples of OPT1 and OPT2 will be passed to the char strict options argument for agent onload. The options argument is encoded as a modified UTF-8 string. If option is not specified, a zero length string is passed to options. The lifespan of option string is the agent onload or agent onload agent libname call. If needed beyond this time, the string or parts of the string must be copied. The period between the agent onload is called, and when its return is called on the onload phase. Since VM is not initialized during onload phase, the set of allowed operations inside the agent onload is restricted. The agent can safely process the options and set the set event callbacks with set event callbacks. The VM initialization event is received, that is VM init callback is invoked. The agent can complete its initialization. Rationale: the early startup is required so that the agent can set the desired capabilities, many of which must be set before VM is initialized. In JVM DI, the xdebug command line option provided very coarse-grained control of capabilities. JVM PI implementations use various tricks to provide single JVM PI on switch. No reasonable command line option could provide the fine grain of control required to balance needed capabilities versus performance impact. Early startup is also needed so that agent can control the execution environment, modifying the file system and system properties to install their functionality. Return value of the agent onload or agent onload agent libname is used to indicate an error. Any value other than 0 indicates an error and causes termination of the VM. Now we are considering bytecode instrumentation. Assuming that the constructor is initially empty, the constructor could be changed to this. This interface does not include some events that one might expect in an interface with profiling support. Some examples include full speed method enter and exit events. The intermediate The interface instead provides support for bytecode instrumentation, the ability to alter Java virtual machine bytecode instructions which comprise the target program. Typically, these alternations are to add events to the bytecode of a method. For example, to add at the beginning of a method call to myprofiler.method entered. Since the changes are purely additive, they do not modify the application state or behavior. Because the inserted agent code is standard bytecode, the VM can run at full speed, optimizing not only the target program but also instrumentation. If the instrumentation does not involve switching from bytecode execution, no expensive state transitions are needed. The result is high performance events. This approach also provides complete control to the agent. Instrumentation can be restricted to interesting portions of the code, for example, the end user's code, and can be conditional. Instrumentation can run entirely in Java programming language code or can call into native agent. Instrumentation can simply maintain counters or statistically simple sample events. Instrumentation can be inserted in one of three ways. Static instrumentation: the class file is instrumented before it is loaded into the VM, for example, by creating a duplicate directory of *class files which have been modified to add instrumentation. This method is extremely awkward, and in general the agent cannot know the origin of the class files which will be loaded. The next way, load time instrumentation: when the class file is loaded by the VM, the raw bytes of the class files are sent to the instrumentation to the agent. The class file load hook event triggered by the class load provides this functionality. This mechanism provides efficient and complete access to one-time instrumentation. Other one is dynamic instrumentation. A class which is already loaded and possibly even running is modified. This optional feature is provided by the class load hook event, triggered by calling retransform class function. Classes can be modified multiple times and can be returned to original state. Mechanism: the mechanism allows instrumentation which changes during course of execution. The class modification functionality provided in this interface is intended to provide mechanism for instrumentation. The class file load hook event and the retransform classes function, and during the development for fix and continue debugging, the redefine classes function. Care must be taken to avoid perturbing dependencies, especially when instrumenting core classes. For example, an approach to getting notification of every object allocation is to instrument the constructor on object. Assuming that the constructor is initially empty, the constructor could be changed to this. However, if this change was made during class file load hook event, then this might impact a typical VM as follows. A first created object will call the constructor, causing a class load of myprofiler, which will then cause object creation, and since myprofiler isn't loaded yet, infinite recursion, the resulting in a stack overflow. A refinement of this would be to delay invoking tracking method until the save time. For example, track allocations could be set in the handler for the VM init event. The set native method prefix allows native methods to be instrumented by use of wrapper methods. Now we are considering accessing functions in functions. When used from the C language, the double indirection is used to access the functions. The environment pointer provides context and is the first parameter of which function call. For example, JVMTI error get loaded classes, JVMTI env pointer env and jinit asterisk class count pointer. Sorry, jinit asterisk class count ptr, jinit class ptr, return, and here the return an array of classes loaded in the virtual machine. Number of classes in the array is returned via class count pointer, and the array itself via classes pointer. The native code accesses JVMTI features by calling JVMTI functions. Access to JVMTI functions is by use of an interface pointer in the same manner as Java native interface JNI functions are accessed. JVMTI interface pointer is called environment pointer. An environment pointer is a pointer to an environment and has the type JVMTI env asterisk here. An environment has information about its JVMTI connection. The first value in the environment is a pointer to the function table. The function table is an array of pointers to JVMTI functions. Every function pointer has every function pointer is at a predefined offset inside the array. When used from the C language, double indirection is used to access the functions. The environment pointer provides a context and is the first parameter of a function call, for example, here. When used from C++ language, functions are accessed as member functions of JVMTI env. The environment pointer is not passed to the function call, for example, here. Unless otherwise stated, all examples and declaration in this specification use the C language. A JVMTI environment can be obtained through JNI invocation API get env function. Each call to get env creates a new JVMTI connection and thus new JVMTI environment. The version argument of get env must be JVMTI version. The return environment may have different version than the requested version, but the return environment must be compatible, the get env will return jni underscore e version if a compatible version is not available. If the compatible version is not available, then JVMTI is not supported, or JVMTI is not supported in the current VM configuration. Get env will return jni underscore e version. Other interfaces may be added for creating JVMTI environments in a specific context. Each environment has its own state. For example, desired event, event handling functions, desired events, event handling functions, and capabilities. An environment is released when with dispose environment. Thus, unlike JNI, which has one environment per thread, JVMTI environments work across threads that are created dynamically. Now we are considering single step in event index in events. The void init call single step JVMTI env pointer JVMTI environment JNI environment pointer JNI underscore event environment JThread thread JMethod ID method JLocation. The single step events allow the agent to trace thread execution at the finest granularity allows by the VM. A single step event is generated whenever a thread reaches a new location. Typically, a single step event represents the completion of one VM instruction as defined in the Java virtual machine specification. However, some implementation may define location differently. In any case, the method and location parameters uniquely identify the current location and allows the mapping to source file and line number when that information is available. Now we are considering data types. Here JBoolean holds a Java programming language Boolean unsigned 8-bit. Now we are considering constant index. Here the JVMTI class status array. The value is 16. The bits value is 16, and the class status flag. Class is an array. Here, class is an array. The JVMTI class status array. The value is 16. Here, the class is an array. If set, all other bits are 0. An example, we can consider this one, this exception in C language. This is a asynchronous exception object of type J object in stop thread. As an error example, we can consider JVMTI error. This is in C or C++. This is type JVMTI error. This holds an error return code You can see the type declaration here, type def. As an example 2, we can consider this one, error server being server debug worklight, error cannot load this JVMTI agent twice, check your Java command line for duplicate JDWP options. Error occurred during initialization of VM. This is occurred in the environment of with Eclipse plugin IBM Worklight Developer Edition. Now here you can see the structure of the JDWP agent. To serve the here we are discussing command execution. To serve as a bridge between the debugger and the target JVM, the JDWP agent implements the command execution flow. In this flow, the transport manager acts as a gateway for all incoming and outgoing packets. The packet dispatcher thread the packet dispatcher reads incoming commands, wraps them and transfers to the command dispatcher to find the appropriate command handler. These handlers actually execute commands and then send reply packets to the debugger via the transport manager. Note the command handlers normally return control after executing the command, with the exception of asynchronous handlers. The latter start the separate thread to execute command and return control immediately. Asynchronous handlers are used for JDWP commands that may last long and can be interrupted. For example, invoke method. Asynchronous handlers send reply packets to the debugger via transport manager. After completing the command, if an error occurs during command handling, that corresponding module forms an error reply packet and send it to the debugger. This figure shows the dependencies between major JDWP agent components. Lines show dependencies between components of the agent. Red lines are for generating events, and black lines for command execution. Here you can see debugger is connected to transport manager. Transport manager, package, packet dispatcher, command handler, event callback, request manager, and event dispatcher are inside the JDWP agent. Here the transport manager is connected to packet handler. Packet handler is connected to command dispatcher. Command dispatcher is connected to command handler. Command handler is connected to JVM here, JVMTI. Here JVM TI is connected to event callback. Event callback is connected to request handler. Here command handler is connected to request. Event callback is connected to request manager. Here command handler is connected to request manager. Request manager is connected to dispatch manager. Dispatch manager is connected to transport manager. Now we here you can see the testing framework in JDWP tests. This figure shows the structure of JDWP test. As shown in this figure, the supplied JDWP tests go through the following life cycle. One, the JUnit framework launches a test that initializes JPDA testing framework. 2, JPDA framework starts the target JVM according to the specified configuration and establishes a JDWP connection using a default or specified transport. A synchronization channel. 3. A synchronization channel is established between the debugger and the Debuggee virtual machine if required. 4. The testing method is invoked that performs testing of specific JDWP commands. And events sending JDWP packets over the established JDWP connection. Or using the using the VM mirror wrapper. The test can use the synchronization channel to synchronize its execution with Debuggee class. 5. After the completion of the testing or generating an error, the testing framework terminates the Debuggee. Debuggee JVM and closes all resources used for this testing session before the next session starts. This eliminates the problems with busy socket ports, often JVM processes, or excess running threads when several tests run in a bundle. JUnit test must follow the naming policy closely linked with the name and structure of the class being tested. JDWP tests have no Java classes to be tested. Instead, JDWP test operates with the JDWP commands and events, so it makes no sense to name them according to JDWP command names and group them according to JDWP command sets. The following scheme is used for naming JDWP tests: org.apache.harmony.jpda.test.jdwp.commandset.command test, and org.apache.harmony.jdwp.test.jdwp.events.event test. If several tests are used for one command that require different debugger application, the tests are implemented in separate classes and the numerical suffix is added for the class name. For example, org.apache.harmony.jpda.test.getValues001 test.java, org.apache.harmony.jpda.test.getValue002 test.java. Each JDWP test specifies the Debuggee class to be run in a target JVM. Depending on particular test case, tests can share the Debuggee class or require individual Debuggee classes. Here you can see Debugger VM and Debuggee VM. Here test JPDA framework and VM mirror and connections are inside Debugger VM. Test debugger part is connected to JPDA framework. JPDA framework is connected to VM mirror. Mirror is connected to connection. Here test Debuggee part, JPDA framework, JDWP agent and transport are inside Debuggee VM. Here JPDA framework in Debugger VM is connected to JPDA framework in Debuggee VM via sync channel. Here the connection interacts with transport via send. Here the test Debuggee part is connected to JPDA framework and JDWP agent is connected to transport here. Here now we are considering JDWP agent command flow while running the JDWP agent. This here we describes the typical flow of the JDWP agent when handling commands received from the debugger. As shown in this figure, the command packet passes the following stages. 1. The transport manager reads the packet and forwards it to the packet dispatcher. The packet dispatcher wraps the packet with the command wrapper and forward it to the command dispatcher. 3. Command dispatcher reads the header of the command packet to identify the JDWP command type, create an instance of the corresponding command handler and passes packet to its handler for execution. Depending on the command handler type, one of the following happens. For synchronous command, the synchronous command handler reads data from the command packet, execute the command and store the reply data in the reply packet and return it to the packet dispatcher. The dispatcher then sends the reply packet to the debugger via the transport manager. For the asynchronous command handler, where saves the command wrapper for the processing, start internal threads to execute the command and returns the control immediately. Started threads execute the command, as in this case of the asynchronous handler, and send the reply packet back to the debugger via transport manager. 5. Certain commands handlers interact with the request manager to create or destroy an event request. In this case, the request manager enables or disables the event callbacks for corresponding JVM TI events. If an error occurs, corresponding exception is thrown on any phase, and the calling module stores error info in the reply packets and send it to the debugger via transport manager. This is not shown in the picture in order to simplify the overall scheme. Note this figure is simplified not to show that request manager and the command handler call into an object manager and thread manager to get the object IDs and the thread info. These calls into the thread and the object manager are equally relevant for command and event packet flows in the JDWP agent. Here you can see a transport manager, packet dispatcher, command handler, request manager, and JVM TI. Transport manager is connected to packet dispatcher via read packet, and packet dispatcher is connected to command dispatcher via wrap command. Command dispatcher is connected to command handler via execute command. Then command dispatcher is connected to JVM TI via JVM TI functions, and here the JVM TI is connected to command handler via result. And here the command handler is connected to request manager via create request. Request manager is connected to itself via store request, and here request manager is connected to JVM TI via enable event, and JVM TI is connected to request manager via result. Request manager is connected to command handler via result. Command handler is connected to dispatch manager via reply. Command dispatcher is connected to packet dispatcher via reply, and packet dispatcher is connected to transport manager via send reply. Now we are considering event flow in JDWP agent. Here we describes a typical sequence of an event passes inside the JDWP agent. As shown in this figure, an event passes the following stages. 1. JVM TI callback forwards the raised event to the request manager, which actually contains the appropriate event handler. 2. The event handler creates an event composer object around the event packet and fills it with the corresponding data using object manager. Several events for different event requests can be grouped into the event packet if required. The request manager passes the created event composer to the event dispatcher. 4. The event dispatcher extracts the event packet and send it to the debugger via transport manager. If required by an event event suspended policy, the event dispatcher uses the thread manager to suspend the thread sending the event. If an error occurs during generation of a packet, this event is ignored and warning message is printed to the log output. This is done because the JDWP specification does not provide means for reporting event errors. Here you can see a JVM TI, request manager, event composer, object manager, event dispatcher, thread manager, and transport manager. JVM TI is connected to request manager via callback, and request manager is connected to event composer via create. Here the event composer is connected to object manager via map object ID, and my object manager is connected to event composer via result, and event composer is connected to itself via store data. Event composer is connected to request manager via sequence event packet. Request manager is connected to event dispatcher via post event packet. Event dispatcher is connected to thread manager via via the suspended thread, and thread manager is connected to event dispatcher via result, and the event dispatcher is connected to transport manager via send event packet, and transport manager is connected to event dispatcher via result. Event dispatcher is connected to request manager via destroy, and request manager is connected to JVM TI via continue. Now we are considering the layout of each packet look like this. Here JDWP packets. The JDWP packets JDWP is packet based and is not stateful. There are two basic packet types: command packets and reply packets. Command packets may be sent by either debugger or target VM. They are used to debugger to request information from target VM or to control program execution. Command packets are sent by the target VM to notify the debugger of some event in the target VM, such as a breakpoint or exception. Reply packet is sent only in response to command packet and always provides information success or failure of the command. Any reply packets may also carry data requested in the command, for example, data value of the field or variable. Currently, events sent from the target VM do not require a response packet from the debugger. JDWP is asynchronous. Multiple command packets may be sent before the first reply packet is received. Command and reply packets headers are equal in size. This is to make transport easier to implement and abstract. The layout of each packets look like this. All fields and data sent via JDWP should be in big endian format. First three fields are identical in both packets. Now we are considering command and reply packet fields. Shared header fields, length. The length field is the size in bytes of the entire packet, including the length field. The header size is 11 bytes. So the packet with no data would set this field to 11. ID. The ID field is used to uniquely identify each packet command reply pair, each packet command reply pair. A reply packet has the same ID as the command packet to which it replies. This allows asynchronous commands and replies to be matched. The ID field must be unique among all outstanding commands sent from one source. The ID field must be unique along all outstanding commands sent from one source. Outstanding commands originating from the debugger may use the same ID as outstanding commands originating from the target VM. Other than that, there are no requirement on allocation of IDs. A simple monotonic counter should be adequate for most implementation. It will allow 2 to the power 32 unique outstanding packets and is the simplest implementation alternative. Flags are used to alter how any command is queued and processed and to tag command packets that originate from the target VM. There is currently one flag bits defined. Future versions of protocol may define additional flags. 0x80 reply packet. The reply bit when set indicates that the packet is a reply. Command packet header fields, the command set. This field is useful to means for grouping commands in a meaningful way. The sun-defined command sets are used to group commands by the interfaces they support in the JDI. For example, all commands that support the JDI virtual machine interface are grouped in a virtual machine command set. The command set space is roughly divided as follows: 0 to 62 sets command to this set of commands sent to the target VM. 64 to 127 sets of commands sent to the debugger, 128 to 256 vendor defined commands and extensions. Commands. This field identifies the particular command in the command set. This field together with the command set field is used to indicate how command packets should be processed. More succinctly, they tell the receiver what to do. Specific commands are presented later. Reply packet header fields. Error code. This field is used to indicate if the command packet that is being replied to was successfully processed. The value of 0 indicates success. A non-zero value indicates an error. The error code returns may be specific to each command, but it is often mapped to a JVMTI error code. Data. The data field is unique to each command set command. It's also different between command and reply packet pairs. For example, the command packet that requires a field value will contain references to the object and field IDs of the desired value in its data field. The reply packet's data field will contain the value of the field. Here you can see the command packet your header and under header length 4 bytes, ID 4 bytes, flags 1 byte, command set 1 byte, command 1 byte, and then data variable. Here the reply packet under header length 4 byte, ID 4 bytes, flags 1 byte, error code 2 bytes, and then data is variable. We are focusing on communications channel. The communications channel is the link between the front end and back ends of the debugger. It can be thought of as consisting of two mechanisms. One, a connector. A connector is a JDI object that is the means by which a connection is established between the front and back ends. JPDA defines three types of connectors. Listening connectors. The front end listens for an incoming connection from back end. Attaching connectors. The front end attaches to an already running backend. Launching connectors. The front end actually launches the Java process that will run the Debuggee code and the backend. To a transport. A transport is the underlying mechanism used to move bits between the front end and the back end. The transport mechanism is used. The transport mechanism used is unspecified. Possible mechanisms include sockets, serial lines, and shared memory. However, the format and semantics of the serialized bit stream flowing over the channel is specified by the Java debug wire protocol JDWP. Here you can see JDWP messages follow a simple structure. JDWP defines messages involved in communications between the debugger and Debuggee. The JDWP is packet based and is not stateful. There are two basic packet types: command packets and reply packets. Command packets may be sent by either the debugger or the target VM. They are used by the debugger to request information from the target VM or to control program execution. Command packets are sent by the target VM to notify the debugger of some event in the target VM, such as a breakpoint or exception. A reply packet is sent only in response to a command packet and always provides information success or failure of the command. Reply packets may also carry data requested in the command, for example, the value of the field or variable. Currently, events sent from the target VM do not require a response packet from the debugger. JDWP is asynchronous. Multiple command packets may be sent from the first reply packet is received. Command and reply packet headers are equal in size. This is to make transport easier to implement and abstract. The layout of each packet looks like this: command packet, header, length 4 bytes, ID 4 bytes, flags 1 byte, command set 1 byte, command 1 byte, data is variable length, reply packet, header, length 4 byte, ID 4 byte, flag 1 byte, error code 2 bytes, data variable length. All fields and data sent via JDWP should be in big endian format. The first three fields are identical in both packet types. Shared header fields here. Length. The length field is the size in bytes of the entire packet, including the length field. The header size is 11 bytes. So a packet with no data would send this field to 11. ID. The ID field is used to uniquely identify each packet command reply pair. A reply packet has the same ID as the command packet to which it replies. This allows asynchronous commands and replies to be matched. The ID field must be unique among all outstanding commands sent from one source. Outstanding commands originating from the debugger may use the same ID as outstanding command originating from the target VM. Other than that, there are no requirements on the allocation of IDs. A simple monotonic counter should be adequate for most implementation. It will allow 2 to the power 32 unique outstanding packets and is the simplest implementation alternative. Flags are used to alter how any command is queued and processed, and to tag command packets that originate from the target VM. There is currently one flag bits defined. Future versions of the protocol may define additional flags. 0x80, a reply packet. The reply bit, when set, indicates that packet is a reply. Command packet header fields here, command set and command. Command set, this field is useful as a means for grouping commands in a meaningful way. The sun-defined command sets are used to group commands by the interfaces they support in the JDI. For example, all commands that supports the JDI virtual machine interface are grouped in a virtual machine command set. The command set space is roughly divided as follows: 0 to 63 sets of commands sent to the target VM, 64 to 127 sets of commands sent to the debugger, 128 to 256 vendor defined commands and extensions. Command, this field identifies a particular command in a command set. This field, together with the command set field, is used to indicate how the command packet should be processed. More succinctly, they tell the receiver what to do. Reply packet header field, error code. This field is used to indicate if the command packet that is being replied to was successfully processed. A value of 0 indicates success. A non-zero value indicates an error. The error code returned may be specific to each command set command, but it is often mapped to a JVM TI error code. Data. The data field is unique to each command set command. It is also different between command and reply packet pairs. For example, a command packet in a command packet that requests a field value will contain references to the object and fields IDs for the desired value in its data field. The reply packet's data field will contain the value of the field. Here you can see the request packet. Request header and data are in request packet. Length, ID, flags, set, command set and command are in header. Here you can see the reply packet, header and data are in reply packet. Length, ID, flags and error code are in header. As an example, we can consider Java Debug Wire Protocol. The Java Debug Wire Protocol, JDWP, is the protocol used for communication between a debugger and the Java virtual machine VM, which it debugs. Hereafter called the target VM. JDWP is optional. It might not be available in some implementations of the JDK. The existence of JDWP can allow the same debugger to work in a different process on the same computer or on a remote computer function, remote computer. As an example 2, we can consider this one. This is the last step of some of the 5 steps when faced with an open JDWP service. Arbitrary command execution is exactly 5 steps away. These steps are: 1. Fetch Java runtime reference. 2nd, set up breakpoint and wait for notification, a synchronized call. 3rd, allocating a Java string object in runtime to carry out the payload. 4, get runtime object from breakpoint context. This is 5. Look up and invoked ex easy method in runtime instance. The final step is simply looking for the execution ex easy method in the runtime static object obtained for the 4th step and invoking it by sending an object reference invoke method packet with the string object. As an example 3, we can consider virtual machine command. Create string creates a new string object in the target VM and returns its ID. Out data is a string UTF. UTF-8 characters to use in the created string. Reply data type is string ID and name is string object. Created string instance of java.lang.string. Error data, the value is VM_dead. The virtual machine is not running. As an example 4, we can consider to debug an application using JDWP. The Java debug via protocol JDWP is very useful for debugging applications as well as applets. Step 1, to debug an application using JDWP. Step 1, open the command line and set the path environment variable to jdk/bin, where JDK is the installation directory of the JDK. Step 2, use the following command to run the application called test in this example. Which you want to debug. On Windows, it's Java -xdebug-xrun jdwp :transport equal dt_shmem, command address equal debug, server equal y, suspend equal y, test. On Oracle server and Linux operating system, it's Java -xdebug -xrun jdwp :transport equal dt_socket, address equal 8888, server equal y, suspend equal y, and test. The test class will start in the debugging mode and wait for the debugger to attach to it at address debug on Windows or 8888 on Oracle, Solaris and Linux operating systems. Step 3, open another command line and use the following command to run JDB and attach it to the running debug server. On Windows it's jdb-attach debug. On Oracle, Solaris and Linux operating system it's jdb-attach 8888. After JDB initializes and attaches to test, you can perform Java level debugging. Step 4, set your breakpoints and run the application. For example, set the breakpoint at the beginning of the main method in test. Run the following command: stop in test.main run. When the JDB utility hits the breakpoint, you will be able to inspect the environment in which the application is running and see if it's functioning as expected. Number 5 is optional, and to perform native level debugging along with Java level debugging, use native debuggers to attach to the Java process running with JDWP. On Oracle Solaris, you can use the DBX utility, and on Linux, you can use the GDB utility. In Windows, you can use Visual Studio for native level debugging as follows. Step 1, open Visual Studio. Step 2, open the debug menu, select attach to process, select Java process that is running with JDWP. Step 3, on the project menu, select settings and open the debug tab. In the category drop down list, select additional DLLs and add the native DLL that you want to debug. For example, test.dll. Open the source file, one or more of test.dll, and set your breakpoints. Step 5, type cont in the JDB window. The process will hit the breakpoints in Visual Studio. As example 5, we can consider this example here. For example, to launch the JVM with debug options, to listen on an address, we use this following options with the Java executable. The -agentlib : JDWP with comma separated key value sub options instruct the JVM to load the JDWP agent and wait for a socket connection on port 8000. Here's what each sub option does. Transport equal DT underscore sockets tells the JDWP agent to use socket transport. Server equal Y means that the JVM will listen for a debugger to attach to it. Suspend equal Y means JVM will wait for the debugger to attach before executing the main class. This is also the default value. If set to N, the JVM will immediately execute the main class while listening for a debugger connection. address equal 8000 specified the address at which the debug socket will listen. In this case, the JVM will listen at the port 8000 for incoming connection only from the local host. Starting at JDK 9. Here dash agentlib colon JDWP and equal suboptions loads the JPDA reference implementation of JDWP. This library resides in the target VM and uses JVM TI and JNI to interact with it. It uses transport and JDWP protocol to communicate with the separate debugger application. Transport suboption, name of the transport to use in connecting to debugger application here. Server suboption, if Y listen for a debugger application to attach, otherwise attach to the debugger application at the specified address. Suspend suboption, if Y VM start event has a suspend policy of suspend underscore all. If N VM start event has a suspend policy of suspend underscore none. Address suboption, transport address for the connection. If server equal N, attempt to attach to the debugger application at this address. If server equal Y, listen for the connection at this address. As an exception, here we are considering a package com.sun.jdi.connect.spi in module jdk.jdi. This package comprises the interfaces and classes used to develop new transport service implementations. Now we are considering developing a transport implementation in Java debug via protocol transport interface JDWP transport. The JDWP transport.h Java debug via protocol transport service provider interface. A transport library can be developed using any native language that supports C language calling conventions and C or C++ definitions. The function data type and constant definitions needed for using JDWP transport interface are defined in the include file JDWP transport.h. To use this definition, add the Java C include directory to your include path. Now we are considering transport startup. The callback argument is the is a pointer function. The callback argument is a pointer to a function table of memory management routines that transport must use to allocate the memory for return values that are allocated by the transport implementation. The function the type def is struct JDWP transport callback void strict allocate in jint num bytes and etc. This is the JDWP functions called by the transport. call this for all allocations and call this for all deallocations. The transport library must export an onload function with the following prototype here. The function will be called by JDWP or other agent when the library is loaded. The JVM argument is the JNI invocation interface obtained by agent by invoking JNI's getJava VM function. The callback argument is a pointer to a function table of memory management routines that transport must use to allocate the memory for return values that are allocated by the transport implementation. The lifespan of the callback argument is the onload function and therefore the transport must take a copy of the function table in the JDWP transport onload function. The function table has two entries. The alloc function allocates an area of memory. It has a single argument to specify the number of bytes to allocate. It returns a pointer to the beginning of the allocated memory, or null if the memory request cannot be honored. If the number of bytes requested is 0, then null is returned. If the free function deallocates an area of memory that was previously allocated using alloc function, the memory management functions provided by the agent are thread safe, and the transport implementation is not required to synchronize calls to these functions. The implementation of memory management functions are guaranteed not to call any JDWP transport function. The version is the version of the transport interface that the agent expects. This must be specified as JDWP transport underscore version underscore 1 underscore 0. env is a pointer to the function pointer returned by the function. The JDWP transport onload function returns JNI underscore OK if the transport initializes successfully. If the initialization fails, then one of the following errors are returned: JNI ENO mem, JNI E version, JNI E exist, JNI E enom is returned if there is insufficient memory to complete initialization. JNI E version is returned if the version of the version argument is not JDWP transport underscore version underscore 1 underscore 0. JNI exist is returned if the transport only supports a single environment and the environment pointer was previously returned by the first call to the onload function. Now we are considering attach in connection management in functions. The function GWP transport error attach GWP transport env strict env constant char pointer or char strict address JLong attached timeout JLong handshake timeout attaches the debugger. Attaches the debugger. Attaching to a debugger involves two steps. First, a connection is established to the specified address. Once connection is established, a handshake is performed to ensure that the connection is indeed established to the debugger. Handshaking involves the exchange of ASCII string to JDWP handshake as specified in the Java Debugger protocol specification. The address argument is a pointer to a string representing the address of the debugger. The exec format is specified to the transport. In the case of a TCP/IP based transport, address may include hostname, port number of the debugger. In the case of transport that supports connections through a serial port, it might be the device name. It might be the device name of the serial port. The attached timeout argument specify a timeout to use when attaching. If the transport supports the attached timeout, and if the attached timeout is positive, then it specify the timeout in milliseconds, more or less, to use when attaching the debugger. If the transport does not support an attached timeout, or if the attached timeout is specified as 0, then a timeout is not used when attaching. The handshake timeout argument specified a timeout to use when the handshaking with the debugger. If the transport supports a handshake timeout, and if the handshake timeout is positive, then it is specified the timeout in milliseconds, more or less, to use when the handshaking with the debugger. Exact usage of the handshake timeout is specific to the transport. For example, one implementation may use the timeout as an intercharacter timeout while waiting for the JDWP handshake message from the debugger. Another implementation may use the timeout to indicate that the total duration allowed for handshake exchange. In general purpose of the handshake timeout is to allow for error handling in the event that support connects to something other than the valid debugger. If the transport does not support the handshake timeout, or if the handshake timeout is specified as 0, then a timeout is not used when handshaking. This function returns a universal error or one of the following errors: JWP transport error illegal argument, JWP transport error illegal state, JWP transport error to IO error, JWP transport error timeout. JWP transport error illegal argument is returned if the address is invalid or timeout is negative. JWP transport error illegal state is returned if the transport is currently in listen mode, or there is already an open connection to the debugger. JWP transport error IO error is returned if there is an error other than attached timeout attaching to the debugger. Note that errors during the startup handshake, including the handshake timeout, are considered IO errors. IO errors are specific to the transport. Get last error can be used to obtain string representation of the error. JWP error timeout is returned if the transport supports an attached timeout, and if the attached timeout value is positive, and if the connection to the debugger cannot be established within the attached timeout period. Now we are considering read packet in IO functions. The function JWP transport error read packet JWP transport env asterisk env and JWP packet pointer packet reads a JWP packet from an open connection to a debugger. Reads JWP packet from an open connection to a debugger. This function does a blocking read on an open connection. It blocks indefinitely until a complete JWP packet can be returned, or in the case of transport based on a stream-oriented protocol and the end of stream is encountered. The packet argument is the address of the JWP packet structure that is populated by this function. The packet.type packet.type .cmd cmd dot len or packet dot type dot reply dot len field depending on the on if the packet is command or reply packet is populated with the length of the packet. If the end of stream is encountered, the length field will be set to 0, and all other fields in the packet will be undefined. If the end of stream is encountered after the reading sum, but not all byte of the packet is considered an IO error, and JDWP transport error to IO error will be returned. In the case of the length field will not be populated. When the entire packet is read, then all fields in the packet are populated with values in the host order. This may or may not differ from big endian order required when transmitting JDWP packets. The packet dot type dot cmd dot data or packet dot type dot reply dot data field depending on the depending on if the packet is a command or reply packet will be populated with null or a pointer to the packet data allocated by this function. Packet data is allocated using a allocation callback provided to the transport when the JDWP transport onload function was called. The caller is responsible to free it. The layout of the packet data, that is the data following the header, if any, is returned to the caller in the byte ordering in which it was received. The read packet function does not do any integrity checking on the return packet except checking that the length of the packet as indicated by the first 4 bytes is greater than or equal 11 bytes. If the length field is less than 11 bytes, then JDWP transport error, IO error is returned. The function returns an universal error or one of the following errors: JDWP transport error, IO error, JDWP transport error, illegal state, JWP transport error, illegal argument. JWP transport error, IO error is returned if the IO error occurs when reading the connection is closed asynchronously by another thread calling close function, or badly format packet length field less than 11 bytes is received. IO errors are specific to the transport. Get last error can be used to obtain a string representing the error. JDWP transport error illegal state is returned if there isn't an open connection to the debugger. JDWP transport error illegal argument is returned if the packet is null. Now we are considering get last error in miscellaneous functions. The function JDWP transport error get last error. JDWP transport environment pointer env and char point asterisk msg returns the string representation of the last error. When an error occurs, it is recorded on the per thread basis. Subsequent call to get last error returns a string representation of the last IO error. The MSG argument is a pointer to a null terminated string returned by this function. A string is allocated using the allocation callback pointed to the transport when the JDWP transport onload function is called. The caller is responsible to free the returned string. The function returns a universal error or one of the following errors: JDWP transport error MSG not available. JDWP transport error MSG not available is returned if this thread has not encountered an IO error, or then there isn't a string representation of the last error available. Now we are considering universal errors. The error JDWP transport error none. No error has occurred. This is the error code that is returned on successful completion of a function. Now we are considering example scenarios in service provider interfaces in Java platform debugger architecture. The service provider interfaces and native transport interfaces are expected to be used by the following classes of users: debugger and tool vendors that need to develop new launching connector implementation or wish to provide additional support options for remote debugging over and beyond the TCP/IP and shared memory transport provided by Oracle. And the next point, embedded device, operating system or virtual machine that require remote debugging using transport than TCP/IP. Now we are considering developing a connectors that wish to make use of Oracle provided transports should load the transport service using code such as following. The class transport service in package com.sun.jdi.connect.spi in module jdk jdi, a transport service for a connections between a debugger and a target VM. Developing a connector involves creating concrete implementation of launching connector, attaching connector, or listening connector. Every connector implementation must have a public no-arg constructor in addition to implementing the connector methods. The constructor will be called by the Java virtual machine manager during initialization. The constructor may be a no-op, or it may perform initialization tasks such as loading a transport service. The constructor does not throw any checked exceptions, so any problems during initialization should be thrown as an error or other unchecked exceptions. Connections are not required to use transport service. Some connectors may connect to the target VM using a mechanism other than transport. For connectors that use transport service transport service implementation of the connector can either reference transport service implementation directly or it can load the implementation at runtime. Connectors that wish to make use of Oracle provided transport should load the transport service using code such as following. The JavaScript implementation are not required to include Oracle socket or shared memory transport service implementation. So in the above example, error will be thrown if the transport service does not exist. Assuming that the connector is known then the following item should be noted when developing the implementation. The list of connector.arguments should be carefully considered. Some connector implementation, the default argument construction and pairing may be the bulk of the code in the implementation. A connector is required to name the transport that it uses. If the implementation uses existing transport service, then the recommended transport name is the name of the underlying transport service. That is, the connector's transport implementation returns a transport for which the name method returns the java.lang.string representation representing the name of transport. The most connector implementation will establish the connection to a target VM. Once established, the connector's launch, attach and accept method will return a virtual machine instance to the debugger. To facilitate the creation of virtual machine, Mirror the virtual machine manager has a method to create virtual machine. Now we are considering deploying a connector. In order to deploy this, you create a file meta-inf/services/com.sun.jdi.connect.connector similar to the following. To deploy a connector, required a packaging the classes for the connector implementation into a jar file along with the service configuration file that lists the fully qualified class name of the connector. The jar file is then deployed in a location that is visible to the system class loader. The service configuration file must be included in the jar file is named meta-inf/services/com.sun.jdi.connector.connector. The file simply lists the fully qualified class names of the connector included in the jar file. The multiple connect implementation may be included in the same jar file. And in that case, the class name for each connector is listed in the separate line. Suppose you wish to deploy a launching connector named simple launch connector. In order to deploy this, you create a file meta-inf/services/com.sun.jdi.connect.connector similar to the following here. This service configuration file is then packed into a jar file along with the classes that comprises the implementation of the connector. The jar file is then copied into the location that is visible to the system class loader. Once deployed, the connector will be located by the debugger when the debugger is restarted. That is, the simple launching connector will be included in the list of connectors returned by the virtual machines managers all connectors method. In addition, as this is a launcher connector, it will also appear on the list of launching connectors returned by the launching connectors method. Now we are considering developing a transport service. Developing a transport service requires developing two components: a concrete implementation of com.sun.jdi.connect.spa.transport service, a debugging side shared library that implements the JDWP transport interface. The development of transport service requires a high degree of familiarity with the transport and underlying communication protocol. The transport service essentially binds JDWP to an underlying communication protocol. The service that it provides is reliable, and JDWP packets are exchanged between the debugger and Debuggee without duplication or data loss. Given that the packets must be exchanged in a reliable manner might mean that additional protocol support must be included in the transport service or beyond that provided by the underlying communication protocol. For example, if the Debuggee over a raw and unreliable serial connection is required, then the transport service implementer may be required to build in error detection and recovery in the implementation to ensure that JDWP packets can be reliably transported between debugger and the Debuggee. Now we are considering deploying a transport service. In the case of a transport service, com.sun. Serial transport service, then the service configuration file will be similar to the following. The transport service is deployed. A transport service is deployed in a similar manner to the connector. Deploying a transport service required packaging the classes for the transport service implementation into a jar file, along with the service configuration file that lists the fully qualified class name of the transport service. The jar file then is deployed on a location that is visible to the system class loader. The configuration file must be used in the jar file is named meta-inf/services/com.sun.jdi.connect.spa.transport service. As per connector deployment, the configuration file may list the classes names of multiple transport service implementation in the event that the jar file includes multiple implementations. In the case of transport service, that com.sun.serial transport service, then service configuration file will be similar to the following. The service configuration file is then packaged into the jar file along with the classes that comprise the implementation. For example, we will assume that the implementation involves a number of classes. As per the deployment of connectors, the jar file is then copied into the location that is visible to the system class loader. The transport service may have native methods or rely on other APIs that requires a native library. In that case, the native library must be the location that allows it to be loaded using system.load library. The native transport library is loaded by the JDWP agent. It must be located in the normal runtime library path for the operating systems. For example, on Solaris and Linux, or Linux systems, it must be search path specified by the LD library path environment variable. Serial line transport here. Now we are considering Java Debugger protocol and the overview in Java Debugger protocol. The Java Debugger protocol, JDWP, is the protocol used for communication between debugger and the Java virtual machine VM which it debugs, hereafter called the target VM. JDWP is optional. It might not be available in some implementation of the JDK. The existence of JDWP can allow the same debugger to work in different processes on the same computer or on remote computer. The JDWP differs from the many protocol specification in that it only details format and layout, not transport. The JDWP implementation can be designed to accept different transport mechanism through a simple API. A particular transport does not necessarily support each of the debugger target VM combinations listed before. The JDWP is designed to be simple enough for easy implementation, yet it is flexible enough for future growth. Currently, the JDWP does not specify any mechanism for transport, rendezvous, or any directory services. This may be changed in the future. It may be addressed in separate document in the documentations. The JDWP is one layer within the Java Platform Debugger architecture, JPDA. This architecture also contains high-level Java Debug Interface, JDI. The JDWP is designed to facilitate efficient use by the JDI. Many of its abilities are tailored to that end. The JDI is more appropriate than JDWP for many debugger tools, particularly those written in Java programming language. Now we are considering JDWP startup. A handshake process has the following steps. Debugger side sends 14 byte to the VM side, consisting of the 14 ASCII characters of the string JDWP handshake. The VM side replies with the same 14 bytes JDWP handshake. Now we are considering shared header fields in command and reply packet fields. The shared header fields field length. The length field is the size in bytes of the entire packet, including the length field. The header size is the 11 bytes, so a packet with no data would set this field to 11. Now we are considering byte in detail command information. The common data type byte, a byte value, size is 1 byte. Now we are considering virtual machine command set in Java Debugger protocol details. The version here the version command returns a JDWP version implemented by the target VM. The version string format is implementation dependent. We can consider the exception. This is a thrown exception in reply data in tagged dash objects ID in invoke method command in JDWP protocol. As an error example, we can consider this one. Fatal error in native method JDWP no transcripts initialized JVMTI error equal agent underscore error underscore transcript transport underscore init error transport error 202 connect failed connection refused error JDWP transport DT underscore socket failed to initialize transport underscore init jdwp exit error agent error underscore error underscore transport underscore init, no transports initialized. Now we are focusing on front end. The debugger front end implements the high level Java debug interface JDI. The front end uses the information from the low level Java debug via protocol JDWP. As an example, we can consider jdk.jdi module defines the Java debug interface. The Java debug interface JDI is a high-level Java API providing information useful for debuggers and similar systems needing access to the running state of a usually remote virtual machine. As example 2, we can consider this code segment. Here, prepare connector set class to debug and launch VM. Here request VM to trigger event when hello world class is prepared. If this class if this is class prepare event, then set breakpoint. If this is a breakpoint event, then read and print variables. Here disable the breakpoint event here and get values of all variables that are visible and print. As an example 3, we can consider interface event. An occurrence in a target VM that is of interest to a debugger. Event is the common super interface for all events. Examples include breakpoint event, exception event, class prepare event. When an event occurs, an instance of event as a component of an event set is included in the virtual machine's event queue. This is in module jdk.jdi and this is in package com.sun.jdi.event. As an example 4, we can consider this in TIBCO configure Java debug interface JDI. For each TIBCO business events engine you want to enable for remote debugging, perform following actions. Open the be/bin/be-engine.tra file for editing. specify the port on which you want the engine to listen using the environment variable tibco.env.jdi_port. For example, tibco.env.jdi_port 5192, where 5192 is the default value. If multiple engines run on the same machine, ensure that each has a unique port. Uncomment the following line -x run jdwp transport equal dt_socket, address equal %jdi_port %, suspend equal na, server equal y. Start or restart the engine with the -d or -debug command. As an example, we can consider class VM mismatch exception thrown to indicate that the requested operation cannot be completed because a mirror from one target VM is being combined with a mirror from another target VM. This is in module jdk.jdi. This is in the package com.sun.jdi. As an error example, we can consider this one: JDI event dispatch java.land.null point exception. This is occurred in environment with Eclipse Indigo EE. User interface. The user interface to the debugger is not specified. The intent is that tool vendors will provide value-added implementation. As an example, we can consider this one, invoking Java DT. Here you can invoke the Java DT debugger as follows. Note this -class path option controls the class path for the hello application. Once the window appears, you can issue the run command to begin execution immediately. It is also possible to give the class name in the run command, in which case it may be omitted when invoking the debugger from the shell. The class path may also be set from within the debugger using the class path command. As an example 2, we can consider this one. Run and debug. The debugger extension provides multiple ways to run and debug your Java application. This is in Visual Studio and with the extension Debugger for Java extension. This is the end of my. Now we are considering JDB. Here the start a JDB session. For example, if your application's main class is my class, then use the following command to debug it under JDB. You use JDB command and its options to find and fix bugs in the Java platform programs. In the synopsis here, these are options. This represents JDB command line options. Here the class name. This represents the name of the main class to debug, and the argument that is not shown here. Represents the argument that are passed to the main method of the class. The JDB is simple command line debugger for Java classes, JDB command, and its options called the JDB. JDB command demonstrate the Java platform debug architecture and provide inspection and debugging of local or remote JVM. To start a session, there are many ways to start a JDB session. The most frequent used way is to have a JDB launch a new JVM with the main class of the application to be debugged. To do this by substituting JDB command for the Java command in the command line. For example, your application main class is my class. Then use the following command to debug it under JDB. When it started in this way, JDB command calls the second JVM with the specified parameters, loads the specified class and stop the JVM before executing the class first instruction. Another way to use the JDB command is by attaching it to a JVM. That's already running. Syntax for starting JVM to which the JDB command attaches when JVM is running as follows. This loads in process debugging libraries and specify the kind of connection to be made. You can then attach the JDB command to the JVM with the following command. 8000 is the address of the JVM. The my class argument isn't specified in the to a JVM, and all of them are supported by the JDB command. Java platform debug architecture has additional documentation on these connection options. This is end of my presentation. Thank you very much for watching it.